We have found over 6,000 exoplanets, planets orbiting other stars out there in the universe. We've studied the atmospheres of some of them, we've mapped their temperatures, detected storms raging on them, and even found water vapor in the atmospheres of some of them. But here's the thing that keeps us astrophysicists up at night. It's the fact that we've still not yet managed to take a direct image of an Earth-like planet. Despite all of our recent advancements in telescopes, building them ever bigger and bigger, the direct detection and imaging of exoplanets can still only give us images of massive Jupiter-like planets orbiting really far out from their stars. Why? Because it's just really hard to do. Stars are so incredibly bright that they drown out the very faint reflected light that comes off their planets. It's like trying to detect someone holding up their phone with their torch on, standing next to a stadium floodlight from miles away. But a brand new paper by Soliman and collaborators has proposed a new way of doing this in the most sci-fi way possible. Not with a bigger telescope or a better camera, but with a giant 99-meter wide space umbrella. The technical term is starshade, and the idea is that you block out the light from the star so that you have a hope of detecting the very faint light of the planet next to it. So in this video, we're gonna dive into this new research and the idea of a starshade, and chat first about why we can't directly image Earth-like exoplanets yet. Then second, how a giant starshade could help. Third, why Soliman and collaborators think this could now work. And then finally, how does this compare to what other telescopes are doing? Like NASA's Habitable Worlds Observatory that also wants to image Earth-like exoplanets, but in a different way. But before we dive into all of that, you all saw how I had an amazing time on my trip to Joshua Tree National Park last month, where I enjoyed some beautifully dark night skies. Now, the planning for that trip was made so much easier thanks to all of the new features on Opera, the sponsor of this week's video. I am one of those people that will just constantly keep opening new tabs on my internet browser, so much so that it just becomes impossible to find anything. So I think my favorite feature of Opera by far is the tab islands. You know, I can group all my Airbnb options in one island. I can then group the recommendations for hikes I've found in another, and then keep it all separate from my research on what I'll be able to see in the night sky when I'm there in another island. I can collapse and expand them, I can name them, and even choose different colors for each one. I've also found Opera's split screen feature so helpful as well. Like, I can have a star chart open on one side while I look at a list of Messier objects I can see from Joshua Tree on the other. I can even split the screen into 4 so I can have my research notes and like the weather forecast open at the same time. Plus, I'm very easily distracted by other apps, so as soon as I swipe away from my browser window, my attention is gone. So I love the fact that I can control my music without interrupting my browsing with Opera's detachable player. I can pop this anywhere inside or outside the browser window. But by far the most useful feature is Opera AI, which has just had an upgrade so that it's smarter, more powerful, and faster. It can help you find sources for information that you read on the web, which is so useful when I'm doing research for my latest night sky news videos. You don't even need to open another tab or have an Opera account to use Opera AI. It's all inbuilt and free. So download Opera today using the link in the description down below. A big thanks again to Opera for sponsoring this video. And now let's start with why can't we directly image Earth-like exoplanets yet? Right, to understand this, I need to get across to you just how incredibly difficult this is. And obviously at its simplest, it just boils down to the fact that stars give out light and planets don't. We can only see the moon and the planets of the solar system in the sky because they reflect the sun's light back to us. But the giant Jupiter is still 9 million times fainter than the sun, and Earth is over 1 billion times fainter than the sun. So taking an image of even a Jupiter-sized planet, never mind an Earth-like planet around a star many light years away, is incredibly difficult. Because to detect such a faint light from the planet, you have to take a really long exposure where you leave the telescope open to detect light. But then what happens is you end up detecting too much light from the star, and it saturates those pixels of your image that then bleed over into the neighboring pixels, which is where you'd expect to find the planet. That's why the majority of exoplanets are found indirectly, either through the transit method, where we wait for a planet to pass in front of its star and we detect the dip in the star's brightness, or by watching whether a star wobbles due to the pull of a planet's gravity that's orbiting it. So if instead we want to directly detect exoplanets, take an image of a star and reveal its star system, then we have to get a little bit clever and use something like a coronagraph. Something inside the telescope itself which blocks the light of the star before it reaches the detector. We can then expose for a really long time to detect the faint reflected light of the planet. Hubble has a coronagraph, as does the James Webb Space Telescope, JWST, and both of those telescopes have managed to directly image exoplanets before. Hubble's even managed to image the same planets multiple times, so that we can actually make a time lapse of them orbiting around their stars. But every planet that we've managed to do this for so far have been absolutely huge. All of them have been more massive than Jupiter. And each of those planets orbits their star further out than Saturn orbits the sun in the solar system. Often they're also found around really young stars, which means the planet is also young. It's just formed, so it's still hot from that formation. It's glowing with its own heat in infrared light, which makes it easier to spot, at least with the James Webb Space Telescope. An Earth-like planet, though, old, cool, and rocky, orbiting much closer into its star, is a completely different kettle of fish. It's much too faint and far too close into its star for our current generation of telescopes with their coronagraphs to be able to detect. So what do? Well, one idea is that we ditch the coronagraph entirely and break out the big space umbrella. Which brings me to part 2. How could a giant starshade in space help us detect Earth-like exoplanets? So the idea is, instead of putting a small mask inside a telescope up in space, you put a giant mask up in space and combine it with a telescope on the ground. NASA are now funding the development of a giant starshade known as the Hybrid Observatory for Earth-like Exoplanets, or HO, first proposed by Mather and collaborators in 2019. And the plan is for it to be a whopping 99 meters in diameter. For context, JWST's sun shield is the size of a tennis court, and that's only 21 meters wide. And that was an engineering marvel that it unfolded without any issues up in space. This starshade would be 5 times wider than that and come with its own set of headaches. But it's also not just a perfect circle shape. It's a flower shape, with a 50-meter wide central region that's ringed by 48 petals, each 24.5 meters long. That shape is really important because it will minimize the amount of light that actually leaks from behind the mask, at least compared to how much light leakage you get with a coronagraph. The light will bend around the petal's shape, but what will happen is that it'll actually meet up and interfere with itself so that it cancels itself out, in the same way that noise-cancelling headphones work to cancel out nearby sounds. Now, don't worry about, looking up at the stars at night and seeing a patch blocked out by a giant space umbrella, because this thing is going to orbit the Earth at about half the distance to the moon. And at that distance, what you can do is angle it so precisely that it can cast a single star shadow onto an observatory on the ground. And what's really cool about this is that you can design it so that the shadow actually forms above the Earth's atmosphere, which means that the starlight is blocked before that weak signal from the reflected light of the planet even passes through the Earth's atmosphere. And it's the atmosphere that's really scuppered attempts to directly image exoplanets from the ground before, and it's why we tend to use space telescopes with coronagraphs to do this. The Earth's atmosphere smears out the light in your images. Think about turbulence on an aeroplane and you shaking because you're going through a patch of rough air. Light from very distant objects also passes through that rough air and gets smeared out. It's quite literally why we sing "Twinkle, Twinkle, Little Star." What it means is that any faint signals especially just get smeared out and lost in the noise. Unless you can correct for the smearing that the atmosphere does. That is what's known as adaptive optics. You fire lasers into the atmosphere to record what happens to the tiny laser dot and then subtract those effects off the image to get the sharp crispness back. And this is why ground-based telescopes are now starting to contend with space-based telescopes, especially because we can build a much bigger telescope on the ground than we can fit into a rocket and launch into space. And the bigger the telescope, the fainter the thing that you can see, and the smaller the thing that you can see as well. You have the resolution to be able to split out two separate objects that are very close together, that otherwise with a smaller telescope would just blur together. So there's lots of excitement for the European Southern Observatory's extremely large telescope, the ELT, which is under construction in Chile and set to come online in 2030. It has a mirror to collect light that's 39 meters across. That's over 6 times bigger than JWST's mirror. Combine that light collecting and resolving power with the new technologies of adaptive optics to correct for the atmosphere, and all of a sudden, taking a direct image of an Earth-like planet starts to sound possible. At least if you have a way to block the starlight. Which brings me to part 3. Why Soliman and collaborators think this could actually work now. So Soliman and collaborators ran some simulations to investigate whether combining the starshade design with the ELT gives you the contrast that you need to be able to detect the very faint light from a planet 1 billion times fainter than its star, but also the resolution you need to be able to separate that planet out when it's orbiting very close in to its star, like the Earth does. That's what this plot shows. You've got the separation of the planet and the star on the horizontal axis, and then the contrast, the difference between the star and planet brightness on the vertical axis. The blue and orange lines show what the ELT combined with the starshade would be capable of detecting at different wavelengths of light. And then the yellow dot there on the edge shows the properties Earth would have to someone about 30 light years from the sun. The fact that those blue and orange lines are below that yellow dot means that the ELT in a starshade should easily be able to image an Earth-like exoplanet. And you can see that in the simulated images that Soliman and collaborators have generated as well of what the solar system would look like if it was 55 light years away and imaged with the ELT in this starshade. You can see Venus, Earth, Mars, Saturn, Jupiter were all detected around the massed light of the star. But those of you who've been following me for a while might remember that NASA is also planning to do something similar with the Habitable Worlds Observatory. Its next generation telescope, the follow-up to Hubble and JWST that's set to launch in the 2040s. Which brings me finally to part 4. How does this compare to what other telescopes are doing? Because yes, JWST has a coronagraph that's breaking records. It's still not capable of imaging an Earth-like exoplanet. And one of the limitations there is because it has a static coronagraph. It can't adapt to correct for the bleed of light from the star. However, the Roman Space Telescope, which NASA is set to launch in late 2026, will have the first active coronagraph, meaning it can achieve contrasts that are 100 to 1,000 times better than what JWST or Hubble can currently do. But Roman still falls short by over an order of magnitude of achieving the contrast needed to image an Earth-like exoplanet. Plus, Roman has a mirror like Hubble's at 2.5 meters wide, so it won't have the resolution needed to image a planet close into its star to really be an Earth-like planet around a sun-like star. Those are really the ones that we care about, that should be in the habitable zone and might have the conditions for life. That's why NASA is also planning for the Habitable Worlds Observatory in the 2040s. And the plan is for HWO to be a 6-meter wide telescope with what's known as an IFU to collect the light. An IFU is where you take an image in each wavelength of light, or you can think of it as a spectrum or a rainbow of light in every single pixel in your image. That's great because that means we won't just directly detect exoplanets that they're there, but we'll also be able to study their atmospheres through the fingerprints that molecules leave behind on the reflected light. To do that for Earth-like planets though, NASA is going to have to aggressively develop coronagraph technology to get down to the contrast needed to detect an Earth-like exoplanet. So realistically, HWO is a couple of decades away. But what Soliman and collaborators argue is that the ELT, in combination with a starshade, can perform better than the targets that have been set for HWO, at least for nearby stars. And that's just because of the sheer size of the ELT, at 39 meters wide compared to HWO's planned 6 meters. And a starshade is going to be a lot cheaper than HWO to develop and launch and maintain as well. So it's likely that we can start directly imaging Earth-like exoplanets a lot sooner than waiting for HWO. So is a giant space umbrella a no-brainer then? Well, maybe, but the catch is you've got to develop it so that you can then fold it up so it'll fit into a very narrow rocket so that you can launch it into space and then it will unfold without any human supervision and hope everything goes off without a hitch. We had to do this with JWST and its mirror and sunshield unfolding had us all in a right tizzy. But at least we know that we can do something that is engineeringly similar. So, whether it is a giant space umbrella or the Habitable Worlds Observatory that gets us there first, I don't think we're that far away from a direct image of an Earth-like exoplanet orbiting around a sun-like star. Maybe a decade or so. At least that is if this NASA's starshade concept continues to get funding, despite the continued threats to cut NASA's science budget. So I really hope this giant space umbrella starshade does go ahead, because even just one image of an Earth-like exoplanet orbiting another star in our galaxy would be absolutely incredible. I mean, don't get me wrong, the image itself won't look that incredible because the faint planet light will just end up being a little fuzzy smudge of a few pixels. But that's what us astronomers absolutely live for. A fuzzy smudge is where science happens. But in a different way. There's a Chinook going over. I will wait. The like double blade thing just makes like such like a bass rumble that I always think it's gonna come across on the mic. It's really loud. It's gonna be crossing forever. Like it's actually rumbling things on my shelves now.